Welcome to my talk. I'll be describing how we provide privacy guarantees for different de-identification techniques in the literature. This work is in collaboration with Harley, Thomas, Dietrich, and first, de-identification is a way of hiding users' information, either through, for example, deletion, or we can replace by non-threatening surrogate. For example, if we have a sentence like, how about Rick's Cafe around noon and 15th. And we assume that Rick's Cafe, noon and 15th are actually sensitive words. One way of addressing this problem is just to delete the sensitive information. Well, as you can see, this is not very grammatical. We lose a lot of information and we don't even know where we have deleted some information. So we can use the Redact approach where we blacken out all this information and at least we know the position where this information has been deleted. We can now explore other replacement strategies. For example, instead of just blacking it out, we can use some placeholder also for the Redact. And we can even categorize the sensitive information into different categories. For example, we can have a PR for personal names, maybe LOC for location, and we can use this to replace sensitive information. So another approach is the name placeholder, where we can replace a sensitive location by an example of a location. And that means every occurrence of something that has to do with location will be replaced by the same thing. For example, we have Frankfurt Airport is replaced by London, and Rome is also replaced by London, which is also nice because it's not realistic. Immediately, people will know that this text has been transformed. A better approach is using word-by-word replacement, where every entity is being replaced by another word of the same type. So, and for example, Miller is being replaced by John, Lufthansa by Bosch, and Frankfurt Airport by New Boston, Rome by Berlin. But sometimes it also affects the fluency, where in this example, we replace 6 p.m. by 11 morning. And it's not very fluent. So a better approach is to replace all multi-word expression like 11 morning by another multi-word expression like 12 p.m. For example, let's assume we have transformed our text. There's still some attacks that can be performed on that can review the privacy or the sensitive information of users. One attack is the untransformed text leakage or the parrot attack. So let's assume we use an automatic way of identifying sensitive words. This is not 100%, but the question is that can we identify the mistakes of the classifier? And Carroll showed in their paper that if you label the transformed data set, and you use it to train a new model, and now use this to predict the tags of the sensitive words. The same mistakes of the original classifier can also be made by the classifier that an adversary used. But the problem is that this approach is very expensive because you have to label data set, and it doesn't scale to large data set. Another attack is that, let's assume we have transformed a text. Can we re-identify the original untransformed text? And how can we provide privacy guarantees for this? And this is our concern in this paper. And we want to know if we can quantify the privacy leakage of perfectly tag sensitive words. That means that the privacy loss should be 0 because if everything was perfectly transformed, then there's no way we can identify or re-identify the sensitive words. And another thing is that can we also provide privacy leakage, or what is the privacy loss for automatically tagged sensitive words? That means we do not perfectly tag the sensitive words. And this is what happens in practice. And sometimes if we transform all the text, it might also affect the utility on downstream NLP tasks. So we want to make this transformation a bit more flexible, or we call it more probabilistic text transformation, where we have a replacement probability, and if we have an application that leads to, that can affect the utility, we can also lower the replacement probability and not replace all the words in the text. So our probabilistic text transformation is like this. So we have an algorithm M that transforms a text, and with a probability 1 minus P, we can decide to keep the token. Our probability P, we replace the token by another token. For example, we can replace Berlin by London. And the algorithm is as follows, that we just randomly choose from a uniform distribution, a small number, and if it's less than our replacement probability that we choose, P, we replace. If not, we do not do anything. And with this algorithm, we can actually provide a privacy loss using differential privacy. Differential privacy is a well-known technique in the literature for analyzing privacy of databases. And so imagine we have two databases that they just differ in one element, especially if it's a very large database. The output you get from one database, one should not be different from database two. So, and using this information, that means a user information in database one and database two, I mean, this kind of statistics you get does not depend on only one user. So if it depends on one user, then there's no privacy for that particular user. And this is the approach we're using. And in our formulation, that means that if we have D1 and D2 as neighboring data set, D2 can just be obtained if we replace a token, let's say a token in D1, T1 by another token T2. So, and D1, D2 just differ in one element. Then we can compute the privacy loss epsilon that the output T, which is a replacement token, is it the same is it the same if we apply the transformation algorithm to D1, and is it the same if we apply the transformation algorithm to D2? And in differential privacy, the lower the privacy loss, the more privacy we have. But if the privacy is too low, it might affect the utility. And because of this, we provide a formula that we can use to compute what is the privacy loss. And this is what is given here. And we can approve this formula just by analyzing what's the probability that the replacement token belongs to the transformation of D1 or the transformation of D2. The first case is that if we assume T1 and T2 are being replaced by T, so the implication is that both, I mean, when you apply the algorithm on database 1 and database 2, they are both transformed. So if they are both transformed and replaced by exactly the same token, then we do not have any privacy loss. So everything is fine. So our epsilon will be 0 because we take the log of 1. But we can have another scenario if we just decide to, either to replace T1 or T2, or even better, maybe our replacement algorithm replaces T1 by another token that is actually the same thing as T1. And in that kind of scenario, we have the denominator, which is exactly the same as case 1, but the numerator has two choices. Either we can keep the probability by 1 minus P, or we replace the probability by P multiplied by the distribution of our replacement token. And for this task, the distribution we use to replace token is just based on the relative frequency of the token in the corpus. So in the Redact case, if we just replace all locations by LOC, then everything is fine. So then we have a privacy loss of 0. And in the case of of word-by-word replacement, again, we are in this situation where we have to control what is P. And if P is 1, everything is being replaced. So the question is that what is the utility of our text transformation? We examined this utility on 3 tasks: name entity recognition, intent classification, and dialogue act classification. And we also examined 6 data sets: verbmobile, ATs, SNPs. These are 2 popular tasks for intent classification. Verbmobile, we annotated the name entities ourselves, and the dialogue art data set was from Microsoft. Yeah. So based on this, we could also compute what's the privacy versus utility trade-off. So based on what we have earlier described, the higher the replacement probability, the lower will be the privacy loss. And if we do not replace a lot of text, the privacy will be high because more of users' information are being exposed. And when we look at the trade-off that if we do a lot of replacement, in the Redact case, actually this results in very low performance. And that's why the F1 score, for example, when the epsilon is near 0, the F1 score is also near 0. So, but in the word-by-word replacement, this is more robust. And even when we have a much lower, epsilon, the privacy loss, we still have very high F1 score. So this is very useful for downstream tasks. We further evaluated this on 6 data sets, and we also find the same thing. So, for example, in the NAR, if we use the readouts or type place or all this placeholder, just drastically reduce the performance. And we found out that only word-by-word gave something that can be used for practical application. And also for the intent detection case, we also saw like reduction in performance for the readout and the other placeholder approaches. And only the word-by-word and entity, full entity replacement gave a performance that is very close to the baseline. And similarly for the dialogue act classification. And based on this, we could conclude that that it's only this word-by-word and full entity replacement that are robust against performance drop across different tasks. And in conclusion, we prove the privacy guarantee for different text transformation techniques, and we show their performance on 6 data sets and 3 NLP tasks. And we conclude that only word-by-word and full entity replacement are more robust to downstream tasks. Thank you.